In section 6.3, we're going to take a look at some examples of real-life situations that can be modeled by these exponential functions that we've been talking about. Typically, we know that in an exponential model, when x goes up by 1, y goes up by some repeated multiplier. So what we'll be looking at is processes that involve that repeated multiplier, because those are the ones that we know will work with our exponential functions. Keep in mind our exponential function in general looks like a times b to the x power. What we'll see is there are a lot of really important applications in this area that turn out to be exponential. Here are a few of them: compound interest, the way medication reacts in your bloodstream or in your body, radioactive decay, and there's many more as well, but those are just a few sort of previews of some of the things we're going to see end up being modeled by exponential functions. So let's take a look at our first example. We have a $10,000 deposit made into an account that pays 4% interest compounded annually, which just means they add the interest once every year. Find an equation that models that situation, and then use it to predict how much we'll have in the account after 15 years. All right, I'm going to go ahead and create a little table of values. And this is a really common strategy that I use. If I'm not given a table of values, creating one can be helpful. So I'm going to let my input here be my time in years. And I'm going to let my output be A, the amount in the account, which would be in dollars. And since we deposited $10,000 at the beginning, I'm going to say at time 0, we have that $10,000. All right, 1 year later, let's think about what happens. So we know that we're going to earn 4% interest. If I take my $10,000 and multiply it by 4%, looks like I'm going to earn $400 in interest during that first year. And of course, I still have the $10,000 I started with. So I actually have $10,400. All right, let's go to the end of the second year. I'm still earning the 4% interest. And this time, since I started with $10,400, I'd earn 4% interest on that amount. So this year, I'm going to earn $416. Plus, I still have that $10,400. So I end up with $10,816. All right, I'm going to continue my chart out one more year. $10,816. I'm going to earn 4% interest on that. So multiply that by 0.04. $432.64 interest this year. Add the $10,816 that I had. And we're now at $11,248.64. And of course, we could keep on going from there. But I want to think about this just a little bit differently. If that all makes sense, I now can say my model, A of t, would be A times B to the t power. And I can definitely start right out by saying the little a value is 10,000, right? The starting amount is the $10,000. Now, since my t values are going up by 1, there should be some constant multiplier that allows me to go from a value to a value each year. You may already know what it is, but I'm going to use a calculator to find it just in case. If I were to take the 10,400 and divide by the 10,000, It looks like the multiplier that went from here to here was 1.04. Does that continue to work? 10,816 divided by 10,400. Yeah, 1.04 again. And just for thoroughness, we'll do the last one. Let's see, last value divided by 10,816. And there we go. There's that 1.04 again. So my constant multiplier here is 1.04. Oops, not 5, 4. And that means that my base is 1.04. So I can write my function as 10,000 times 1.04 to the t power. All right, let's talk just a little bit more about the a and the b values for that model and see whether we think we maybe could have predicted those without ever having made that table of values. Certainly the a value, the 10,000, being the starting amount, would have been predictable. So in terms of what a and b are and what they mean, a, the 10,000, is the starting amount. That is how much I had at time t equals 0 at the beginning. B is the 1.04, right? I'd like to think just a little bit more about why that number was 1.04. If you think about this problem again, we were earning 4% interest every year. And 4%, of course, is the 0.04 part. But where did the 1 come from? Well, the 1 actually represents the fact that I get to keep 100% of my money that I had the year before, plus I get an extra 4%. So I actually have 104% of what I had last year. So when I think about that B, think about it as a percent. If you move the decimal 2 over, right, 1.04 becomes 104%. It's 100% that we keep from the previous year plus 4% increase in the interest each year. So we're going to use that idea to say, you know what, maybe we don't actually have to write down a table of values for every problem. We can certainly predict the A value as long as we know how much we started with. And we can even predict the B value by saying, well, however much we're increasing or for that matter decreasing by, if we just add the 100% that we keep from the previous line, we'll have our percent, which we can then change back to a decimal, and we know the B. So here's a summary of that at the top of the next page. In our exponential model, f of x equals a times b to the x. Again, a represents the starting value when x, or whatever your independent variable is equal to 0. B isn't exactly the relative rate of change, but it's very closely related to the relative rate of change. Right? If we know the percent rate of change, we simply add the 100%, that was how much we were bringing over from the previous line, and then convert it to a decimal to find our B. Conversely, if we knew B, we could actually figure out the relative rate of change by just taking out that 100%, and that would give us the percent rate of change. All right, we'll shelve that last line for a little while. We're going to mostly work with this one in the next couple of examples. All right, so in example 2, A school district has experienced a 6% annual growth rate since 2005. The district had 750 students in 2005, and we would like to write a function that gives the number of students, S of t, in the district t years after 2005. So we're looking for S of t equals ab to the t. And I know a couple of things. The a value really has to be that 750 because that was the starting number of students in the beginning year, 2005, right? Which is the t equals 0 year. The b value, well, we have a 6% annual growth rate. But remember, just like with the money, we don't get rid of the students from last year, right? We're keeping them. So we have to add 100% of the students from the year before to that 6% growth rate to say our b is 106%, or moving the decimal, 1.06 in decimal form. So I can get the a and the b pretty much just from the information in the problem without having to make that whole table of values. And my S of t, the number of students, is now 750 times 1.06 to the t power. All right, we've really kind of already explained, I probably laid this out poorly. We've already explained what a and b are and what they mean, but again, real quick, the a is 750, and that was the number of students in 2005, which was our starting year. And then the b value, 1.06, really represents 106%, which is the 100% that we keep from the previous year, plus the 6% increase. For each year. All right, and then the last part of this problem, find the number of students in the district in 2011. So let's see, we started in 2005. That would be a t value of 6. And that's just a matter of plugging 6 into our function. So S of 6 we'll round off to the nearest whole number of students would be 1005. All right, we're going to do one more same kind of problem. We should be able to predict our A and our B just by reading. In this example, 1960, there were about 100,000 black rhinos. The world population of black rhinos decreased by about 7.5% each year from 1960 through the mid-1990s, when conservation and anti-poaching laws began to bring that population back from near extinction. Our goal first is to just write a function that gives the number in thousands of black rhinos t years after 1960. So I'm going with n of t equals a times b to the t. I'm going to be smarter this time, and I'm going to write the information about my a. Well, actually, we'll go ahead and put it in here. A is the starting population in 1960. And they told us that was about 100,000. So I'm going to go in thousands. And we'll let A be 100. And then our B value, well, we're decreasing by 7.5% each year. So that would be negative 7.5% added to the 100% from the previous year. So we're at 92.5% of last year's amount as we decrease. And the decimal form of that is 0.925. So my function n of t is going to be 100 for A times 0.925, our B value, to the t power. And again, just kind of turning the tables, I know we've already written it up here, but if you saw this equation and didn't have the earlier information, you could actually look at that A and B value and reconstruct the situation by just saying A is 100, the starting population, in 1960 was 100,000. And B is 0.925, or 92.5%. In this case, if I have to think, well, if I compare that to 100, it's kind of like subtracting 100, right? You'd have a negative 7.5% rate of change, relative rate of change. And that's that 7.5% decrease each year. It's really the same as the last time. It's just a little bit harder to break it down the way I did it, right? With the 106% here, really I took 106% minus that 100% to get the 6%. I'm doing the same thing here. 92.5%, subtract the 100% that we started with to get that negative rate of change in this case. All right, the last question is to predict how many, or there's a couple more. Find the number of rhinos in 1985. So 1985 would be 25 years after 1960. So we'd be looking at t equal 25. And so n of 25, 100 times 0.925 to the 25th power. Is about 14.24. And again, that's in thousands. All right, and the last one, if conservation efforts had not begun, would black rhinos actually be extinct by now? So in other words, if my function n continued to be valid because nothing was done to change the situation, would we be down to no rhinos at this point? Well, let's see. I'm making this video in 2022, so if you're watching it later, we're doing this for 2022. In 2022, our t value would be what, 62 years after 1960? So if I find n of 62, I have about 0.796 thousand. Or if I move my decimal 3 places for the thousand, it would be 796 rhinos. So at least according to our model, they wouldn't be extinct. We'd be down to a very small number, but not quite extinction, right? All right. The other part of this question was, according to the model, would the rhinos ever actually be extinct? Well, let's go ahead and think about what that function actually looks like. And I think I have it as my screen behind me here. If I make it small enough, you'll be able to see it. There we go. If I put my function in, n of t is 0.925, excuse me, I forgot my 100, 100 times 0.925 to the t power. And let's see, we're going to need a pretty large window here. So let me expand this a bit and expand this a bit. We can verify a couple of things we just said, right? N of 25. There's that 14.24 that was our prediction for 1985. And then for 2022, we did N of 62, right? There's that 0.795 or 796. So we've gotten down to a very small number of rhinos, but not zero. Think about this graph for a second. Does this graph ever actually become zero? Technically, it doesn't, does it? The x-axis here forms a horizontal asymptote, and the graph gets very close to zero, but it's never actually equal to zero. So in fact, technically speaking, we don't see true extinction in terms of zero rhinos. However, if we got down to just one rhino, right, there's no way it could reproduce. So we could call that effectively our extinction point. Let's see how we could predict where it's just one rhino. I'm going to have to go to the point here where I can actually see there's my one rhino there. Right? And actually, that's not even true. It's 1,000 rhinos, isn't it? What would one look like? Well, let's see. One would be 0.001. So if I add the line y equals 0.001 thousand, that's one rhino. And let's see, is there an intersection point over here? Ah, it's way over here. Predicts we'd be down to one rhino in 148 years, or 147th year. So we'll never see our model become zero, because we know that's what exponential decay functions do, right? They get really close to zero, but they don't actually become zero. But we just predicted that we will have one rhino that is n is 0.001 in thousands, right? Move your decimal over 3 places. That's your one rhino. 147 years after 1960. Now let's see, what is that? 1960 plus 147. That would be in the year 2107. And at that point, of course, without being able to reproduce, we effectively have extinction. It's one thing to remember about these exponential functions when you use them as models, they never actually become zero. Right? They can get very, very small, but they'll never truly become zero or go down to the negative outputs. All right. The next few examples that I want to do are half-life and doubling problems. They're handled very similarly. In some problems, our rate of change isn't exactly given outright, but we're given enough information to find it. This is typically the case in half-life problems, where you're told how long does it take for half of something to decay away, or doubling problems, where you're told how long it takes for something to double. Same idea if it's tripling or quadrupling or whatever. These problems, half-life problems, doubling, tripling, etc. problems, always require exponential models, because can you see that we actually are looking at that constant relative rate of change, right? In a half-life problem, we're cutting something in half over and over and over. The constant multiplier is 1/2. In a doubling problem, we're multiplying something by 2 over and over, or by 3 if we're tripling, and so on. So these kinds of problems we'll always want to use exponential models for. All right, just for a little bit of practice before we do a full problem, we're going to set up a little table for a situation where we start with 50 items, we have exponential decay with a half-life of 15 minutes, right? I don't need to do anything with the table, I just want to set it up just to get a feel for this. All right, so if I set this up, my time t would be in minutes. And I'm going to say n is the number of whatever these items are. And we start at t equals 0 with 50 items. Now the half-life of 15 minutes means that 15 minutes later, the number of items I have is literally cut in half. It's now 25. After another 15 minutes, so 30 minutes in all, this number is cut in half again. It's now 12.5. After another 15 minutes, 45 minutes, cut it in half again, 6.25. Okay. So when you're creating these tables of values for half-life problems, your inputs are going to continually go up by the amount of the half-life, right? Every 15 minutes, I have another half-life. And then the idea of the half-life is your output gets cut in half every time you add another half-life on. Now, I could have done the same thing with a doubling or tripling problem, right? If I knew the doubling time or the tripling time, I just would have multiplied by 2 or multiplied by 3 here instead of multiplying by a half. But it's that half-life time or doubling time or tripling time that tells you how to set up the left-hand column or the inputs for your table. I want to do one more. This one's going to be a doubling one, or tripling one, I guess, actually. We're going to set up a table where we start with 12 items, and we're going to triple it every 2 days. Again, we're just setting up the table right now for practice. So t here is in days. And again, I'm just going to say n is the number of items. And in this problem, we start with 12. So at 0 days, we have 12 items. And then every 2 days, we're going to triple our amount. So after 2 days, we've tripled that. We now have 36. Another 2 days, so a total of 4. We've tripled that again. We now have 108. Another 2 days, so 6 in all. We've tripled again, and we now have 324. So my tripling time told me how to set up the left-hand column. I triple every 2 days, so this is my tripling time. And then because we are tripling, we're multiplying by 3 in my outputs. So that's how you set up tables of values for a half-life problem, a double, triple, quadruple problem, whatever. And that's really important because that's where we're going to start with all of these. Let's just think for a moment about where we would go for there before we do a full-blown example. Because we typically will know our starting amount, we'll know the value of little a in our exponential function. Unfortunately, we don't know b. It's tempting to think we do. It's tempting to think, oh, this is just b as a half, or this is just b equals 3. But unfortunately, notice that my inputs are not going up by 1. So I cannot conclude that that's just the constant multiplier in the b value. Okay? I would have to have these going up by 1 for that to happen. So what we'll do instead is we'll use some of the techniques that we learned in the last section to actually calculate the b values for these problems. All right. Let's do one start to finish now. The half-life of acetaminophen, which is the active ingredient in Tylenol, is 2.5 hours, meaning that if someone takes acetaminophen, the amount that's still in their body is cut in half every 2.5 hours. So let's suppose that a person takes a 500 milligram dose of acetaminophen. I'd like to create the table that shows the way that this is behaving and how much is left in their body for various times. So T in this case will be in hours. And let's see, A, I'm going to say is the acetaminophen, and that was in milligrams. We know at time 0, we originally took a 500 milligram dose. So we're starting with 500. And since the half-life is 2.5 hours, that means that every 2.5 hours, we're going to cut the amount in half. So after 2.5 hours, half of that would be 250. Another 2.5 hours brings us to 5 total. Half of that would be 125. Another 2.5 hours, so 7.5. Half of that, 62.5. I'll do one more. Another 2.5 hours brings us to 10 hours, and that's going to cut in half again, 31.25 milligrams. So there's the table of values that I'm going to use to create my equation, my exponential function, to model this situation. So let's do that. We know A of t is going to look like AB to the t. And as a matter of fact, we already know the A value because we know the y-intercept is 500. So right away I can say A of t is 500. B to the t. To solve for the b itself, I'm going to have to use any one of the remaining points here and plug in for the A of t and the t, and then use that to solve for the b. Now you can use any point you like. I'm going to use 125 just because there's no decimals in it. And I don't know, it just makes me happy to at least start that way. So A of t is 125 equals 500 times v to the 5th power. We'll divide both sides by the 500. 125 divided by 500 should be 0.25. Let's just double check that. Yes, 0.25 equals b to the 5th. And then I need to get rid of that 5th power. I'll use the reciprocal exponent, the 1/5 power. And so 0.25 to the 1/5 power is about 0.758 if I keep 3 decimal places. So my function a of t is 500, that was the a value, times 0.758 to the t power. All right, let's see what we can predict based on that function. What are the values of a and b in our model, and what do they mean? Well, the a equals 500, that was pretty straightforward. That just means we started or took 500 milligrams at the beginning, right? But let's think about what the b value is actually telling us. B is 0.758. Now I'm going to treat this just like I was treating the b's in the previous problems. Remember what we did? Whatever our b value was, we changed it and thought of it as a percent, subtracted the 100% we started with, and what was left gave us the relative rate of change. I'm going to do that same thing here. I'm going to say, if I think of it as a percent, it would be 75.8%. Subtract the 100% that we actually started with. What is that? Negative 24.2%. So what this says is my relative rate of change is the negative 24.2%, or in other words, the amount of Tylenol in the body is decreasing by 24.2% per hour. Okay. You may remember writing phrases very similar to that in the past when we were dealing with linear equations and slope. This is again a rate of change. The difference is slopes were absolute rates of change. They would have told us how many milligrams per hour our amount was being reduced by. But exponential functions are always relative rates of change, right? They always are going to tell us what percent we're changing per hour, per day, whatever your units happen to be. So absolute rates of change were linear. We're now dealing with relative rates of change or percent change per unit of time. All right, the last part of this, it's considered safe to take another dose once the amount of acetaminophen in the body falls below 100 milligrams. Use our model to determine when it's safe to take another dose. And it says we can consider whole numbers of hours only, so we'll round to the nearest whole hour. I'm going to say, I want to know when is n of t less than 100. And I am going to use Desmos to help me solve this. So I'm going to put my, or excuse me, I was using a, not n. When is a of t less than 100? So I'm going to go ahead and I'm going to put my a of t into Desmos, and we're going to see if we can figure out when it falls below 100. So let's see here. A of t was 500 times 0.758 to the t power. And again, we're going to need significantly larger values than this. Okay. All right. So I'm going to also add in the line y equals 100. And we could see that it takes about 3.3 hours to get to the point where we have 100 milligrams in the body. So you'd have to go past the 3.3 hour mark before you should take another dose. So to go past 3.3, if we're only considering whole numbers, we would be at 4 hours. So when is A of t less than 100? For t values greater than 3.3 is what we discovered on the graph. But that means as far as whole numbers of hours, we would want to wait till the 4th hour to take our second dose. All right. Try another one here. Example 5. Beginning in 2005, when there were 1,400 breweries in the United States, the number of breweries approximately doubled about every 5.5 years. We're going to create a table of values again, showing the number of breweries for various years. And again, we're going to kind of choose our t variable strategically to take advantage of the situation. So what I mean by that is, since we know what happened in 2005, let's let t equal years after 2005. All right, so let's make a table here. T again is years. We've already said that's after 2005. And I'm going to go N for the number of breweries. And in 2005, which would be the year 0, we knew there were 1,400. All right, this is doubling every 5.5 years. So after 5.5 years, that amount has doubled to 2,800. Another 5.5 years would bring us to 11 years total. Doubling again is 5,600. And I'll put in one more. Another 5.5 years brings me to 16.5. And that would double again to 11,200. So every 5.5 years, I'm doubling the number. All right, working by hand, we want to find a function that gives the number of breweries in the US. I'm going to say years after 2005, since that's how we defined our function. And if I go with n of t equals ab to the t, once again, we do know the a value right away. A is going to be 1,400. Since my inputs do not go up by 1, I can't predict the B value easily. Instead, I'm going to have to do a little bit of math. And I'm going to pick another year to plug in. Again, you can pick any line from the table. I'm going to go with that one just because it's got whole numbers. And I'm going to say N is 5,600 when T is 11. All right, I want to use that now to solve for my B. So we'll divide by the 1,400. 5,600 divided by 1,400 is 4, equals B to the 11th power. And to get rid of that 11th power, I'll use the reciprocal exponent, the 1 over 11 power. Again, that means when I multiply my exponents, I'll just have B to the first. Of course, if I do that over here on the right, I also have to use the 1/11th power over here on the left. And that should give me my B value. About 1.134. So my N of T function then is the 1,400, the A that we already had, times 1.134 to the T power. All right, the A and the B. The A, the 1,400, again, that was just the number of breweries at the beginning, which for us is in the year 2005. And the B is 1.134. Again, I'm going to treat this just like I have the last couple of times. I want to think of it as a percent. So 113.4%. Subtract the 100%. You think of that as kind of what you started with. And this time I get a positive 13.4%. And that makes sense because this number of breweries is increasing. And now I can say that the relative rate of change, that is the number of breweries, is increasing by 13.4% per year. And again, just like the slope statements, your rate of change statements should make sense if someone were to read this, even if they hadn't seen the rest of the problem. All right, lastly, it says find the number of breweries predicted for the year 2019. So let's see, we're starting in 2005. 2019 would be a T equal 14, right? 14 years after 2005. So if I find N of 14, what am I going to get? About 8142. Since it's number of something, we'll just round to the nearest whole number, 8,142. In actual fact, there were about 8,300 instead of about 8,100. We're still in the ballpark, right? We're only off by a couple of hundred. That's not too bad. So I would still say this is a fairly good prediction. But then it says, do you think that this will continue to be a good prediction? Let's think about what exponential functions do for a moment, even without graphing this really specifically. I know that eventually exponential functions increase very rapidly. Right? It seems like eventually the number of breweries would not be able to keep up with that really rapid rise after a long time. So I'm going to say this is still a fairly good prediction, but long term, I would guess the predictions will be too big. All right, let's stop there. That was our doubling and half-life and tripling and all that good stuff. We'll stop there for this video, and then we'll finish up this section in the next one.